Hi, my name is Georgiy Platonov, and I will be presenting our work on the system capable of answering spatial questions in a physical blocks world. The setup that we're using is depicted in this picture. As you can see, we're using several blocks marked with various corporate logos for unique identification. These blocks are also color-coded using the colored strips running along the block's edges as red, green, or blue. We use two Kinect sensors to track the block positions on the table, as well as various additional I/O equipment for audio-visual communication. The interaction is speech-based. We employ Google Cloud Speech-to-Text API, as well as animated child avatar, David, for communicating with the user. The following video fragment demonstrates the interaction with the system. David?
Hello again.
Which blocks are to the left of the Twitter block?
The target block and the Starbucks block are to the left of the Twitter block.
What is the leftmost block?
Only the target block.
What is the leftmost block?
Only the Starbucks block.
This slide shows the principal components of the system. The block's world tracker reads the data from the Kinect sensors and models the configuration of the physical blocks in Blender. This model serves as a sort of a mental image of the real physical situation that our system uses to make spatial judgments on. The dialog manager, ETA, takes in the user transcript obtained from the automatic speech recognition system and puts it through a specialized custom-built semantic parser that produces a logical form representation of the user's question. A specialized spatial component incorporates Constraint Solver and implementation of the spatial relations. Finally, when the answer for the question has been produced by the Constraint Solver and returned back to the dialog manager, it generates the reply, which is sent to the avatar app to be communicated back to the user. ETA is a dialog manager designed to follow a modifiable dialog schema specified using a flexible and expressive schema language. The main contents of a dialog schema are logical formulas with open variables describing successive steps expected in the course of the interaction, typically speech acts by the system or the user. These are either realized directly as actions or expanded into subschemas for further processing as the interaction proceeds. A key mechanism used in the course of instantiating schema steps, including interpretation of user inputs, is the hierarchical pattern transduction mechanism. Transduction hierarchies specify patterns at their nodes with branches from a node providing alternative continuations as a hierarchical match proceeds. Terminal nodes provide result templates or specify a subschema, a subordinate transduction tree, or some other result. ETA also incorporates the semantic parser that converts the transcripts of the user utterances into the unscoped logical form representation. The ULF is a general-purpose semantic parsing representation that is built on a formal, type-consistent model theoretic foundation close to the surface form of English. It also preserves majority of linguistic phenomena such as tense, aspect, plurality, and so on, using various explicitly defined operators. You can see the example of a ULF for the corresponding English sentence below in this slide, and you can also see some of the mentioned type operators, such as, for example, plurality and tense operator. The ULF representation of the user's utterance is then further parsed into a data structure that we call query frame. A query frame is a hierarchical data structure that is depicted here in this slide that you can see. It consists of various predetermined slots that are occupied by various constraints and modifiers extracted from the ULF representation of the question. These modifiers and constraints include types, determiners, colors, numbers, as well as various intensifiers such as directly, slightly, and so on. This query frame is then augmented with additional information about the type of the question, for example, whether the question is asking for a specific block or a number of blocks that satisfy a certain property or a block color, etc. And then it is passed to the constraint solver for further processing. The query frame is then passed into the constraint solver module, whose purpose is to find the objects that satisfy the constraints contained in the question. Constraint solver works by recursively resolving the predicate and the arguments contained in the query frame. By resolving the predicate, we simply mean mapping the preposition into the function that implements it. And resolving the arguments means finding all the objects that satisfy the argument constraints, such as color, number, type, and so on. Once all the candidate arguments are found, all the possible combinations of these arguments are formed, and the predicate function responsible for that relation is applied to every such combination. The output of the constraint solver is the set of tuples of this form, where the first component is the specific argument combination, and the second component is the confidence level, that is, the value of the predicate evaluated on this specific combination of arguments. Let's consider the following example question with the block configuration displayed on the right. Resolving the argument positions yields the following results. So the first argument, red blocks, is getting resolved to Twitter block and Mercedes block. As you can see from the picture, only Twitter and Mercedes block are red. And the second argument, arg1, is uniquely identified in the question itself, and so the system just returns the corresponding block. Applying the prepositional predicate above to every possible combination of the arguments yields the following values for each specific configuration. From these values, the initial answer set is formed, that you can see below. Finally, the highest value is being filtered out. This exact filtering process depends on the precise wording of the question and the values returned for each configuration of arguments. We model spatial prepositions as probabilistic predicates constructed from sets of factors, which are primitive geometric and functional relations that are usually accompanying or correlate with a specific spatial configuration. These predicates operate on the 3D imagistic scene reconstructed in Blender. Examples of factors are the scale distance between the centers of two objects, whether two objects are in contact, whether they are of certain shapes or types, and so on. These factors then are either linearly combined or maybe the maximum out of them is taken depending on a specific relation. For example, when one object is on another object, it is often higher than that second object and typically supported by it. So these two factors, relative height and support, are contributing to the computation of the relation of on. Not all factors potentially influence a relation are relevant in a given situation, so we check various combinations of them that correspond to different usage patterns or stereotypical use cases. In order to evaluate our system, we instructed several volunteers to ask spatial questions of the general type supported by the system, but without restriction on specific wording. They were requested to mark the system's answer as correct, partially correct, or incorrect. The proportion of correct and partially correct answers is about 80%, which, given the vague and subjective nature of spatial judgments, we find quite satisfactory. We also separately tested the performance of the ULF parser, and you can see the numbers on this slide. I should briefly mention that apart from answering the questions in a static context, we are also adding the capability of answering questions about past states and actions, such as block moves. This both allows for a more meaningful and realistic application of spatial relations and gives the interaction a more dynamic dialogue-like flavor. And that's it. Thank you for your attention.